Hi, welcome back. So this time it's an entirely different topic. It's about uncovering remote peering interconnections at IXPs. And let me just briefly give you some motivation on this topic. So within the IX community, there was a lot of discussion about whether IXP remote peering destroys like some fundamentals of the internet and yeah, it's not meant to be there. And I don't want to go down this road today, but my thinking, or the thinking of this team of researchers from Forth, Lancaster University, DKIX, and AMSIX was actually, okay, but before we can really argue about this, we need to understand what's going on. So actually, how much remote peering at IXPs can we find out there? And as we all understand what an IXP is, one of the main things I want to highlight here again is it should provide direct interconnection among AESs and keeps local traffic local. So at least if you look at public references like Internet Society, where the benefits of Internet exchange points are summarized, those are the key points, right? It reduces cost and it builds a local Internet community. And building on those fundamentals, we also need to keep an eye on the pressure in the market. So there's pressure for diversifying peering, so increasing volumes, more pressure on ISs for denser and more diverse peering connections, and thereby a fundamental shift of peering practices that is required, right? Like the mental model 20 years ago was just, yeah, we have transit and a bit of peering, but now all those big CDNs are not necessarily IXP peering, but a lot of peering and also a lot of IXP peering. And a very high level definition of remote peering is when a network peers in an IXP without having physical presence at the IXP's infrastructure. I mean, I understand that's way more complicated because what is the IXP's infrastructure? If I'm at a co-location on the same campus, is it remote or is it not remote? And how is the game with resellers? So I could connect for financial reasons through a reseller, even though I'm hosted in the same facility. So it's a whole lot of complexity we're facing if we're asking the simple question, how much remote peering is out there? So how to peer remotely? It's connect to the IXP peering fabric without co-locating the route server, that's understood. And the main driver might be equipment, deployment, and operational costs. So equipment, so you don't need multiple routers at different locations and the colo costs and all this stuff. And you can connect through to multiple IXs with the same equipment, with the same router, right? So, but the risk we're running into is remote peering cancels out a lot of fundamental IXP benefits. So it introduces third parties. It reduces the resilience and reliability. So more complexity is always reducing resilience. And it might increase latency. So let me define the goal for this research study. And this was what goes beyond this cable. So we saw that cable, and this is plugged into the IXP platform, but actually we have no clue what's actually behind it. So we want to achieve more transparency, as I explained in the beginning of this talk, and identify remote and local peers from an external view without using proprietary IXP data or using our internal view. So actually, we just want to use public available data sources. And this is beneficial for IXP operators and customer point of view as well. Because as an IXP operator, you don't necessarily know whether someone is a remote peer or not, because this is not in the commercial model of the IXP to really have data on this. And the features of remote peering. So what are the characteristics compared to local peering? And the ultimate question, which eventually was not answered in this research study, but needs a follow-up, is what are the implications on the resilience of the ecosystem? So let's quickly have a look at the state of the art. So today we just have some very fundamental work which only focused on the RTT-based remote peering inference. So they just detect remote peerings based on RTT measurements. And this can be done. Some IXPs offer trace routes or pings through the looking glass, and this is within the fabric or very close to the fabric. And that, yeah, that's how they measured. They used those to really infer RTT-based local or remote peerings. And they just defined a value and said everything with a higher latency than 10 milliseconds is an indication for a remote peer, and then we assume it's a remote peering. It's a conservative threshold for local regional IXPs, because for local this might be true, for regional it might be complicated if there are multiple facilities within the same city and the same layer 2 fabric. But we will now get into this to more detail. So to begin with, we have a validation data set to get some sense of at what we are actually looking. So, and with this regional IXPs data set, we could see that 40% of the remote peers actually have RTT lower than 10 milliseconds. However, 80% of the remote peers have less than 1 millisecond RTT. So it's not as black and white as the previous study has shown, right? So there are a lot of local peers that actually have a higher RTT, and there are a lot of remote that have a lower RTT. However, it gives us, if we look at the distribution, it gives us a fairly good sense to just have an overview of what's going on. And if we focus on wide area IXPs and have a heat map on the RTT between the different ones, we see that 87% of the facility pairs actually have more than 10 milliseconds median RTT. And we used the data from the NetIX for this experiment. And roughly 14% of the IXPs as of today can be classified as wide area IXPs, meaning they cover not just one metropolitan region, but expanded beyond. So our methodology, actually how it works, what we are building. And we propose a first principles approach to infer remote peering and local peers. So first, we want to take into account the port capacity. Because if an AS has a very high port capacity at an IX, it's very unlikely that they're actually remote. So if we talk about hundreds of gigabits, the assumption is that they can't be remote. The next assumption is we're doing RTT measurements with ping, and the RTT values provide some evidence how far an IXP is. So the lowest ever observed RTT gives the indication of the least, or at least this distance is guaranteed. So it can't be further away if we consider speed of light. And then co-location facilities. So we know from a previous study and public available data which co-location facilities hosting which networks. And this gives us also a good data foundation to understand how far or where actually the equipment is. And we have multi-IX routers, as I explained before, one router, multiple IXs. And of course, there's a lot of private connectivity over facilities, which is established without the IXPs being involved. So the algorithm we are proposing just eventually does a very simple thing. So we get an inference whether a peer of an IX is remote, local, or we can't really tell because the data we're seeing is contradicting each other. So the first step, and if we have one of those results, we stop the algorithm. And the first thing is we just focus on the port capacity from IXP websites and PeeringDB. So we know that PeeringDB is a rough indication, and we know that websites are not always up to date, but this gives us at least some ground truth. Then we infer the distance between IXP members and facilities, and that's how we basically build, from our vantage points, an IXP RTT map, which we use, including the facility information. And for the facility information, we also have the GPS locations where actually the facilities are. And correlated with the RTTs, we can really say the physical distance and infer on the latency. So in the last step, we localize the facility level and the private connectivity. So we using, as the step before, but just with the AS2 facility mappings, we're doing trace routing to see which hops we are traversing. And given the order and the different facilities, we can get a clue where a network is sitting and thereby whether it's remote or local. So does it work? Our first summarized results is that we don't really have a good coverage for all the peers we're focusing on in every data set. So sometimes, for example, with the port capacity, we just have 11% coverage. However, this is a very precise metric because it's coming from the network itself. And we didn't have any means to verify the accuracy. So overall, we can say that the coverage is 93%, the precision 95%, and we can have an accuracy of 94% with the validation datasets. So now the question, what are actually the results? How does remote peering look in the wild? And first of all, we want to explain from the 4 steps I explained in the algorithm before, from which actually the inference is coming. And therefore, we are focusing on the top 30 IXPs from 3 days in 2018. And on this plot, you can see, like, as I said, which step of the algorithm actually inferred that this is local or remote. And 10% of the inference can be made using only the port capacity. RTT colocation facilities and multi-IX modules account for the majority of the inference. That's the green part of the plot. And 25% of the multi-IXP routers connect to more than 10 IXPs. So the inference results. So here again, a number of IXPs and the results. So you see the orange part is actually the number of local peers. The yellowish part is number of remote peers. And blue is we could not make inference based on our algorithm. So what we found is that 1/3 of members peer remotely with the IXP. 90% of the IXPs have at least 10% of their peers remote. But for the really large IXPs, such as AMSIX, DKIX, FranceIX, MSKIX, have 40% of their peers remote. And if we focus on the growth rate, therefore we looked at 5 IXPs where we had historical data, and we look at join and departure rates, and we see that actually twice as much remote peers compared to local peers. And remote peers have a far higher join versus departure rate. So the assumption would be a bit that maybe you're more flexible with the remote peering and it's easier to de-peer or to access, but we also have a good number of peers that turn from remote peers to local peers. So, or it could be an indication of a saturation of the system, right? So everyone in this metropolitan region or who has or wants to establish a POP there has it already. And if you want a small capacity and don't want to go into this area, then you rather do it via remote peering. So this is actually, I'm skipping it. Remote peering routing implications. So actually, we were a bit curious about the past. So we also did a traceroute measurement study for remote peers. It was 380 members. And actually, it was done at DKIX Frankfurt. And we saw that 66% of the cases, the traceroutes included the closest IXPs to the remote peer. But in 34% of the cases, we do not comply with the expected hot potato routing exit strategy. However, the hint is this is trace routing, and this can't be considered as ground truth, right? This is rather an indication. So we compiled all the data and all the stuff we have and build a website to really visualize it. Please go there and check it out. However, note this is not the fastest website, and we experienced some load issues this morning already, so maybe you check it rather tomorrow or tonight. And yeah, you can play around with it. You can check out different IXP facilities. You can query for different ASs. And it's showed on the map, and it also gives you an indication whether it is likely to be a remote peer or local peer, and whether it's outside of the RTT range or not. So let me conclude. We built a new methodology to accurately infer peers connected to IXPs through remote peering, and thereby we try to increase the transparency of the peering ecosystem and illuminate peering trends and practices. So the takeaway is a lot more remote peering and faster growing than local peering. Remote peering becomes popular practice in almost everywhere, and we made it publicly available through our web portal. The remaining future work is to really use those inferences to really get some information on how often do the links fail or such things. So if it's increasing or decreasing the resilience of the ecosystem internet, and also have an interpretation of traffic levels, right? It might be that, or it is the case that it's a huge number of remote peers at an IXP, but I'm sure without having proven it that they cannot be accounted for the majority of the traffic at the IXPs, right? So even though we see a lot of remote peers, are they that important if we take the entire internet ecosystem into consideration? So thank you. That's it from my side, and I'm happy to take your questions.
Camilo Cardona from Entity Communication. Hi, so I'm one of the authors of the previous study. Thank you for mentioning the study. So I have one comment there. In our defense, what we wanted was to give a low, like a
lower bound.
Yeah, a lower bound in how much remote peering was used, and we wanted to reduce the number of false positives, and just mention that.
Yeah. I mean, you did a very good job in academia until your paper was published. No one knew about remote peering. When I talked about remote peering, they were like, "What are you talking about?" So
yeah, right.
you got it started. So
yeah,
thanks for that.
So just one question. When we did the study, there was one particular case in which one router I think in Russia, I think it was BK, they had like 9 different remote peering sessions from the same router. And well, we didn't look too much into that, but I don't know if you have any more of this type of curiosities, which I think is fun to know whether is some more of these cases happening of I don't know, n number of sessions from the same routers or stuff like this.
Yeah. So the max we observed was 15 actually, and I wouldn't say commonplace, but it's not super rare. So you can find it here and there, and yeah, it happens. So I guess that's it. Thank you so much. Have a good afternoon.